All right, everybody, welcome. We're going to start talking about momentum today, and here we go. So first up, the momentum is, we use a special character for it. It looks like a P equals mv, mass times velocity. The units for it will be kilograms times meters per second. The other units, just to get it in your notes, is also Newton seconds. Very important, the next one is it's a vector quantity. Energy is not a vector quantity. Energy is what we call a scalar. In other words, it's just a number. Joules can be anything. It doesn't have to have a direction. Momentum does have direction, and you will see in a second, how that comes out to play. Is it possible for a mouse to have a greater momentum than an elephant? Think about it. All right. Yeah, of course. Because what's the momentum of an elephant that's not moving? Mass is huge, right? It's 2,000 kilograms. If it's not moving, its velocity, 0. So its momentum is 0. So what does a mouse have to be doing to have momentum? Moving. So 12 kilogram ball is rolling at 5. So the momentum is mass. 12 times velocity, 5. And so I get a momentum of 60. Now, what about this next one? This next one looks all funky, right? And so this next one is a sled, has a 4 kilograms box on it. It's being pulled with 20 newtons at 30 degrees. Is moving at a constant speed of 5. Momentum is mass times velocity. Mass, 8 plus 4. Velocity, 5. Momentum, 60. Kilograms, meters per second. That's it. Conservation of momentum. If there is no external net force in an object, the momentum is conserved. And so we say the momentum initially equals the momentum at the end. This means object 1, object 2, object 1, and object 2. We're gonna do a couple problems with this to see how it works out. So if we look at it, as this car is moving at the beginning, just the car is moving. And so let's watch just the car here. He goes from a velocity of 60, and he drops down to 20. Since his mass is 1, his momentum is 60 at the beginning. But if you look at the end, he slows down. So what happened to his momentum? It slowed down. So initially, his momentum was 60. The brick initially isn't moving over here. And at the end, it is moving at 20 because it's now on the cart. So its initial velocity is 0, so its initial momentum is 0. So the momentum before is 60. The momentum after, let's look at after. Afterwards, this guy is 20 because he's going at 20 and his mass is 1. So afterwards, his momentum is 20. This guy's momentum is, mass is 2, velocity is 20. His momentum is 40 then. 20 plus 40. Okay. So notice before my momentum was 60. Afterwards my momentum was 60. The momentum before and after has to be the same unless we have a net force on the outside. From the outside. But if there's no external net force, momentum will be conserved. So let's look at this. So what is the velocity of the yellow canoe, Team Coco, after words? So let's look. So they apply a force off of each other. And so we could say before they're not moving. So initially, the momentum of both of the canoes is 0. And then final, I have a velocity for both of them. Okay. So initially it's 0. So initially the mass is 300. The velocity, the mass is 300 for the final. And the velocity is unknown. But the other guy's mass is 600, and the velocity is 10. Solve out the velocity, and you get negative 20. Well, how would it be negative? Because if I say this is positive 10 meters per second, then this is going to be the opposite direction, negative. Okay? So this is why we refer to these as vectors. All right, so now a cannon fires a cannonball horizontally. The cannonball is fired at 45. What velocity is the cannon recoil? The word recoil means as you fire the cannonball this way, the cannon shoots backwards. We refer to that as recoil. And so the momentum initially of the cannon system is 0. So I say 0 initial equals the momentum afterwards, final. So initially it's 0, mass 750, has an unknown velocity. The 60 kilogram ball is moving at 45. Solve for the velocity. And you get negative 3.6. Now, Cannonball then hits a wall and bounces back. What is the change of momentum? Well, how do you find change of momentum? Change of momentum is momentum final minus momentum initial. So the change in momentum for the Cannonball. Not everything, just the Cannonball. Cannonball has a mass of 60. Its final velocity bounces back at 30, so negative 30 minus mass velocity. The initial velocity of the Cannonball is positive 45. Why did I put the negative here? Since it hit the wall at 45 and bounces back at 30, we need to have one of them negative. And I just chose that one to be negative here. Ferry boats. Guys, ferry boats, when it gets to the dock, its momentum is 0. Cars driving off, they now have momentum. So what does the ferry boat have to have? Momentum. So if the car drives off this way, which way is the ferry boat going to go? This way. That's why the ferry boats always have their engines on. Because as the cars drive off, the ferry boat wants to leave. You've done this before in boats. As you step off the boat wants to leave. All right, bullet hits a block of wood that can move freely. So the bullet, here's its mass, wood's, here's its mass. Block and wood move at 0.5 afterwards. So if I think about it, so my initial, does anything have momentum at the beginning? Yes, my bullet. Okay. Afterwards, they are moving together. Okay. So initially, mass of the bullet, 0.005. Velocity of the bullet, we don't know. Afterwards, the mass of the bullet times the velocity afterwards. Since it's stuck in the block of wood, it's going the same speed as the block of wood. And so I can solve for the velocity of the bullet. So this is called ballistics. This is something we will actually do in class. We will actually connect this to a pendulum problem. It's absolutely wonderful. Is energy conserved? The words I'm thinking of are no. So that's the velocity of the bullet initially, 300 meters per second. If you calculate the energy of the bullet before, and you calculate the energy of the bullet and the block afterwards, you'll see that it dropped a lot. Where did all the energy go? Right here. As thermal energy, as deformation. Did it take energy to deform all that? Yes. All right, take a look at this problem. Pause the screencast. All right, welcome back. So a small person is walking across a massive, freely floating raft in the water. Which picture represents the process? 3. Here's why. The raft is much more massive. And so the person will have a velocity, and the raft will have a small velocity in the opposite direction. This will never happen unless it's ice. This will only happen if the masses are equal. It will have the same velocity. This will happen if it's a surfboard, because that would mean that the velocity of the raft is bigger and the person is smaller. Surfboards are lighter than people, unless you're a very small person. Try these two problems out. We'll slap the answers up for you. There's the answers. So Dr. Sloan, so before they have no momentum, afterwards they both have momentum. And so 0 equals 85, and he walks at 2.7. The log is 200, and solve for V. Second one, wide receiver jumps straight up in the air while catching a ball. Defender moving at 8. So before, initially, you have momentum. Afterwards, they're stuck together. And so before, the defender, 82 kilograms, is moving at 8. Afterwards, 82 kilogram guy, 72 kilogram guy, they're moving together. Since they're together, treat them as one. 154. 154. I should have written that. V. All right, that's it. Solve for V, you get 4.3, which is fun. This works for all sizes. As we look at large scale and small sizes, momentum is conserved. You can always account for it. There are two types of collisions. Tomorrow we will talk about this. Inelastic. Inelastic is when they stick. There's deformation. Energy in is always greater than energy out. We will actually do that in the lab tomorrow. Trains coupling. This is an inelastic collision. That's when we hit and stick. So before I have a moving train, afterwards the masses are stuck together, just like that football problem we just did. So the moving train is moving at 3, and it couples. That's the technical word we have. Couples is when they become then stuck together. And so what is the final velocity? So solve it out. There it is. These are two good problems, and there you go. There's the answer. So cool. We'll be working through problems, and yeah, it's going to be a whirlwind. So I'll see you tomorrow.